Hello students, welcome to week 7. So in continuation to our last week's lectures on Maxwell's equations, we are going to start with the differential form of the Maxwell's equations, and we'll slowly begin to solve these Maxwell's equations for a very simple case or a simple scenario. But before that, I think it is important for all of us to familiarize ourselves with the Maxwell's equations. So what do I mean by that? Right? So most students, when asked the question, what are the Maxwell's equations, right? It is often very easy for many students to just recall this from memory and just jot it down, right? But I think Maxwell's equations have to be imbibed by the student a bit more than just rote learning or memorizing the functional forms of these Maxwell's equations, right? So I'm just rewriting the point form for the Maxwell's equations that we derived last week. Right? So remember that the Maxwell's equations are written in this way, right? In some way, I would say this is a compact way of writing the Maxwell's equations, right? So the use of this operator del or nabla in the form of divergence and curls is able to really give a condensed look to the actual equations that we are going to solve, right? So while it is very pretty to write them down this way, it's important that the student knows that these equations, what are the knowns and what are the unknowns, right? So remember, the unknowns in any problem are the electric and magnetic fields, right? Which in this case is represented as the vector field E and B. These are your unknowns. Okay, so how many unknowns is this truly, right? Even though I have just written E vector and B vector, remember each vector requires 3 quantities, right, in order to define it. So Ex, Ey, Ez, Bx, By, Bz in total make up 6 unknowns, right? So I would say right, even though I say E and B as 2 vector fields that are unknown, it is essentially 6 unknown quantities, right? So individual scalar fields Ex, Ey, Ez and Bx, By, Bz are all unknowns that need to be solved in a generic problem. Now what is usually different from one scenario to the next, right? It is the sources that are there in the problem, and these sources come in form of rho and j, right? So rho being the charge density and j being the current density. So rho and j are the knowns, right? So the Maxwell's equations is actually a combination of 4 individual observations or experimental laws, right? Faraday's law, Ampere Maxwell's equation, and then you have the Gauss's law for electric and magnetic charges, right? So even though it looks like there are only 4 equations, right? Remember, if we only had 4 equations and 6 unknowns, that's actually a problem, which means that there is no solution, right? We know that electric fields and magnetic fields exists, and they are uniquely identified in every scenario, right? So seems to be an contradiction, right, at the forefront. If someone asks you how many Maxwell's equations there are, you would say there are 4, and then they would ask you how many unknowns there are, and you would say there are the 2 vector fields, each with 3 unknown quantities making up 6 unknown quantities. The natural question from anyone who has done basic algebra in mathematics is, I need to have as many unknowns as conditional equations, right, governing those variables. So it seems like there is a discrepancy, right? So we have to peer through a little bit, right? So remember the 2 divergence equations. Right? So equations 1 and 2, the divergence actually becomes a scalar, right? So even though there are Ex, Ey and Ez, when the divergence of the vector field E and B is taken, that actually yields a single scalar, right? So equations 1 and 2 are scalar equations, which means that they contribute to only 2 equations, right? So equations 1 and 2 are just as they are, right? 2 equations for our 6 unknowns. Now we have to find 4 more equations, right? Here again we come into a pickle. So equations 3 and 4 are vector equations, right? So we have vector field quantities on both the left hand side and the right hand side, which means that we have 3 equations each for equations 3 and 4, right? So that's a total of, so I get 2 equations plus 3 each for 3 and 4, that's 6 equations, right? So in total, Maxwell's equations encompass 8 equations, right? Now we've sort of overshot, seems very strange, right? So I have 6 unknowns. Earlier I thought I had 4 unknown equations or helpful equations, but then if I look carefully, 2 of them were scalar equations and 2 were vector equations, which now amounts to 8 equations and 6 unknowns. And this, from mathematics, you should know, means that there is no unique solution at all. There are infinitely many possible solutions, but we know that electric and magnetic fields are unique, right? So wherein is the concern here, right? So the way to resolve this is, some of these equations have to have redundant information, right? So that's the only way we can say that Maxwell's equations together can give you unique E and B fields, because even though there are 8 equations on the onset and 6 unknowns, these 8 equations are not giving you 8 pieces of unique information. They are only giving you 6 pieces of unique information, which means there is some redundancy built in, right? And the redundancy that we don't see mapped out in these 4 equations is the equation of continuity, right? Which essentially relates rho and j, right? Right. So remember, in the introductory class in unit 1, we talked about the fact that charges can neither be destroyed or created, right? And then the number of charges in the universe is conserved, right? And then we talked about this conservation principle also with the term locally, right? Which means to say that I cannot have disappearances of charges in one place and appearances elsewhere, right? If a charge were to have decreased in one point and increased in another point, there must have been a flow of charge connecting these 2 points, right? So that is what the equation of continuity says, and this is the point form for that. All it is trying to say is if I were to take a very small volume and there were essentially the charge density within this volume were to change, it must be because of flow of currents into or out of this volume, right? There's no other way. And this is obeyed at every single point, right? So you can see that if dou rho by dou t is positive, that is it's increasing. So if I take an infinitesimal volume in any point in space and I notice that the charge density there is increasing, then I expect currents to be flowing into this point, right? There's no other way that these charges could be appearing at that point, right? Which essentially amounts to there being an inward flux of electrons into this volume or positive charges, right? And an inward flux of positive charges into a volume is essentially negative for the gradient of J. Okay, so we found that there is one equation that essentially removes one of the redundancy, right? So from 8 equations, we really see that there are only 7 equations, right? There is one equation that's tying up equations 1 and 4, right? Interestingly, the answer to this is that there's actually another equation of continuity for magnetic charges, right? So if suppose there were magnetic charges, and magnetic charge densities, right? Although this doesn't seem to be the case, right? In the world we live in, there are no monopoles, right? Which means that isolated magnetic charges don't exist, which means rho m and Jm are 0, right? But nevertheless, right, if there were terms like these, I could have written a continuity equation for them as well, right? But in our case, this just amounts to since rho m and Jm are 0, this just says 0 plus 0 is 0, right? Which is a constraint too, right? Although it doesn't seem to imply a whole lot of information, is just to give you a sense of clarity that there are indeed 6 unknowns and 6 only unique independent pieces of information, right? This is what allows for Maxwell's equations to have a unique solution in any scenario of rho or J you might give. Okay, this will become more and more clear and apparent as we take up some very simplistic scenarios and we look to solve these Maxwell's equations, right? But remember that as students, a lot of them tend to forget what these Maxwell's equations depict, right? So please do not learn this subject as memorization or rote learning of equations, right? Although these vector equations may look daunting, remember they are in principle trying to show a simplified form of writing differential equations,